Here at the Molecular Design Institute, I'm studying bis-4-bromophenylamine 4,4-azobipyridine, abbreviated as BRDPA, to see if we can make it twist and test its optoelectronic properties. Hopefully we can use it in organic optoelectronic devices. Because my compound interacts with oxygen and moisture, we store it in a vacuum. This is called a desiccator. And also because it interacts with light, I wrap it in aluminum foil. So here's my powder and films. Here I can mix my compound with different additives, which are substances that, when you mix together, can enhance certain properties. It can make it twist more, and other beneficial things. So I've tried mixing with Demargum, I've tried mixing with the Canada balsam additive, and polyethylene. And my compound twists much more when you mix it with Demargum. My mixtures here of powders are, like this one is my compound with 5% Demargum, and this one is 20% polyethylene. So it's pretty fun mixing it over here. Here I am mixing BRDPA azobipyridine with 8.6 weight percent Demargum. There are two main ways to make crystals. The first one is to melt them and let them re-solidify into crystalline solid. This is called the melt. The other way is to put them in a solution and wait for them to nucleate. This is called solution processing. I use the melt because it's easier and yields results faster. So this is a Koffler hot bench, and it varies the temperature at which you can put your crystals. So first you have to clean off your tip. So I'm going to do that with a little bit of ethanol. And then you sandwich your powder between two glass slides. So as you can see, there's powder in between the two slides. And then you can melt them. And so you can watch as it turns into a liquid. And then you can cool it at different temperatures to produce different results. So I could cool it at 70 degrees, or 60 degrees, or 80 degrees, and I can vary how much pressure is on it as well by placing blocks on it as it's cooling. We can see our crystals under this microscope. So I've placed the polarizer in and the analyzer in, which means we're looking at it through cross-polarized light. There's some twisting. This is our microspectrometer here, which is just a fancy way for saying that we can analyze the spectrum, or the spectra, of our compounds. So when you place the sample under here, you can then look at how much light it absorbs, how much light it reflects, and how much light it emits. Every week, we've been presenting to each other to bounce off ideas and share results. So here's some of my results from the microscope. As you can see, there's some really nice twisting here. And yeah, so this was overall a success. I found that melting temperature of 140 degrees, cooling temperature of 70 degrees with no pressure, with 8.9 weight percent Demargum as the additive, creates this nice twisting, and this was the best conditions I could get for that. So yeah, as you can see, we can play around with different samples and see which produces the best. Finally, I read a bunch of papers at home, so I know what I'm talking about. I'm very grateful for this research opportunity. It's been a great experience, and I've learned a lot about material science. I'm happy to have made a contribution into alternative ways of making solar cells.